Time for exponents and logs. So exponents are in the form of y equals a number, any number, to the power of x. So for example, y is equal to 2 to the power of x. That number has to be greater than 0. If we make a table of values of y equals 2 to the x, this is what it looks like. Negative 2 is 2 to the power of negative 2. So that's 1 over 2 squared, which is 1 over 4. Just like that. Plug in these other points and find the y values. And now we're doing this to graph it. And with graphs of exponents, the three key points, and even for logs, the three key points are when x is negative 1, 0, and 1. Because what happens is at 0, to any number to the power of 0 is always going to be 1. When it's to the power of 1, it's just the same number. And when it's to the power of negative 1, it's the same number flipped. So 1 over that number. So it's pretty easy to find those points. Now, if we were to graph these points, it looks kind of like this. And remember how your number can be below 0. So for any exponential function, there's no power that you can add to a positive number that makes it negative or 0. So there's always an asymptote, okay, where there's always an asymptote at y equals 0. And so your graph looks like this. Okay, so these are the points negative 1.5, 0 and 1, and 1 and 2. Now with transformations on exponent graphs, it's the same thing all over again, the a, b, h, k values. Now the b and h values, they're on top because they're, remember, connected to the x, and a and k values are connected to the y. So first of all, always remember to factor out your b value. Okay, the x can't have anything attached to it. Whatever is attached to it, factor it out. And with that new equation, what you do, you find its parent function, which is whatever the base is. Okay, so if it was y equals something 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 3 to the x, so like for this equation, 2 4 2x minus 1 plus 9. For this equation, the parent function will be 4 to the power of x. Okay, so we take that and remember our three key points: half, 1, 2, negative 1, 0, 1, 0, 1. And now remember what we did earlier with any transformations, mapping notation. Okay, so we write down all our values. The a value is 2, b value is 2, h is positive 1, flip the sign, k is 2. And then you just plug all those in here for each of these points to get your new points. Okay, after you apply the transformations. So when doing that, you can pause the video and try that for yourself first. Okay, and with doing that, these are the points we get. Okay, so for example, I'll just walk you through one of them. For the first point, your x is negative 1. Okay, your b is 2, your h is 1, then your a is 2, your y for that one is a half, and k is 2. Okay, so you do the calculation and this is your new points. And then these points transform into these points. And now this set of points are the points that you graph. And another thing, remember the asymptote? Way back here, the asymptote that means y equals 0. Well, what does the k value does? If we were to add a k value, it shifts the graph up or down. Okay, so if the whole graph shifting up and down, that means the, what do you call it, the asymptotes also shifts up and down. So now our asymptote is our k value. Okay, so this is our asymptote, y equals 2. For exponents, the asymptote is the k value. We plug the points half and 3, 1 and 4, and 3 halves and 6. I just divided my graph into halves because it's easier to look at. Then we just curve the line upwards. Okay, connected. Wait. Okay, and that's how you graph exponents. Now coming to logs, logs is just another way to write exponents. It's actually the inverse of exponents. We do we write logs to bring the exponent down. Okay, so you know how to in a equation like x 3x equals something 8. To find x, we divide by 3 on both sides, right? Well, why do we do that? Because division is the inverse opposite of multiplication. And just like that, that's why we have logs, because they help us solve for exponents. They're the inverse of exponents. Okay? So that's what logs are. So let's do a little example. How would you write 2 to the power of x equals, what do you call it? Equals 24, or wait, 32. Well, we write log base 2, then the answer comes in front. That's called the argument. The argument cannot be negative, okay, right? Because remember, in our graph, in our exponents, the base couldn't be negative, so any answer we got couldn't be negative either. Equals x. So all this is saying is 2 to the what power is 32. So log 2 of 32 will be, well, to the power of what is 32? 5. So just like that, try this. Log 3 of 27. All that is saying is 3 to the power of what is 27? Well, 3 to the power of 3 is 27. And logs are in this form. So to take, wait, actually, let's go over this first. So just like a square root symbol, when there's nothing here, that means we automatically know that it's going to be a root 2, right? Whenever something doesn't have a power, we automatically know it's 1. Well, when there's just a log with no base, we automatically know that it's base 10. So let's do an example. Log x equals negative 3. Well, that's saying log base 10x equals negative 3. So that means 10 to the power of negative 3 equals x. And so x is 10 to the power of negative 3, which is 1 over 1,000. We'll get to the solving later though. The main point of this is that log without any base is log base 10. And just like that, we're going to learn this later. And honestly, this is only used in word problems really. uh, or solving, but solving, everything we do for normal logs, we will do for ln. Ln is just log base e. Okay, e is just another irrational number, like pi is just a number, 2.718 something something something. But anything that we can do with logs, we can do with ln. Is just another log. Okay, just remember that. So I won't get into it too much except for the word problems where we need it. Ln is only used for is mostly used for continuous compound interest. Well, in grade 12 at least. So now graphing logs. Take this for example. This is how a parent function for a log looks like. the base is where the number comes in. Okay. And remember what I told you? Logs are the inverse of what do you call it? Exponents. So the inverse of this is y equals 2x. And go back to lesson 1. What does inverse mean? It just means you're flipping the y and x. So for this table of values, whatever the x and y is, you just flip them. So negative 2 and 1/4 becomes 1/4 and negative 2. Negative 1.5 becomes a half and negative 1. Okay. And just like how these were your key points for exponents, because they're easy, the same exact ones are the key points for logs, except now the negative 1, 0, and 1 is in the y. Okay, so when your y is negative 1, 0, and 1, your x is a half, 1, and 2, or 1, well, yeah, whatever you would do. So I guess the easiest way is to just know this and then flip it. And how it would look like if we graph these points. Now the graph looks like this. And with basic logs, you know how I said the argument cannot be negative? So now instead of y, our x cannot be negative. Okay. So that's why we have an asymptote. Instead of y equals 0, it's at x equals 0. So this is just the inverse graph. It's just this graph flipped 90 degrees almost, because that's what inverses do, if that makes it easier to think about. Transforming logs, it's the exact same thing. You just have the a, b, h, and k values. Okay. So for this one, we would take the base function, which is log 2x. Take the 3 key points that we always use, pull out the mapping notation, and find new points. Okay. And now the only thing that's different is our asymptote. Remember how it used to be our k value? Well, that's when it was attached to the, what do you call it? The y. Now it's attached to the x. The x has an asymptote. So what's the horizontal shift of a function? Is the h value. So now our asymptote is going to be our h value. And then once we plug these points in, we can just connect them, and our graph, oh, wait, our graph looks like this kind of. Okay. So that's graphing logs. Now with exponents and logarithms rules, we already know the exponent rules, right? If you multiply two numbers, you they add. If you divide, you subtract. Power to a power is you multiply. Well, that's the same thing, almost the same thing in logarithm rules. If the argument's being multiplied, you can split it up and add it. If it's being divided, you can split it up and subtract it. And if it's to the power, okay, we can take that power out. Okay. So an example question would be like this using log laws. We're trying to combine this into one log. How would we do that? Well, first of all, we're gonna take these, turn them into powers. Okay. So it becomes log h to the power of a half plus log m minus log k squared minus log d. And just to make it look nicer and do a little bit of review, what does to a power of a half mean, or a fraction? Well, a half power means whatever the denominator is the root, and whatever the numerator is the actual power. And anything to the power of 1 is just that. So it's just root h. And now we combine it into one log. So all the positive ones are being multiplied, and all the negative one are being what do you call it, divided. So it becomes log root h times m over k squared times k squared d, because k squared d is being divided. Okay, so that's how you do basic log questions. Now there's one more log law, and this law is used for calculators, calculating stuff in your calculator. Because if you look at your calculator, most calculators can't do a base. Most calculators only have the log and the ln button, and so we need to be able to convert any log into a normal log base 10. And to do that, we follow this log. So log a of b is just log of b divided by log of a. Okay, and this base can be anything. But since for our calculators have 10 as a base, just the normal log, we just use normal logs. So log 2 of 6 becomes log 6 divided by log 2. You plug that into your calculator and you get the answer. That's it. Now let's go to solving. So there's four versions of solving. And first one is the normal exponential solving that we did last year too. This is when you make the same base. So if you can, try to first make everything the same base. Okay. So as you can see, that base right now is looking like 3. So what we do is first convert everything to a power of 3. So this becomes 3 to the x. This is 3 to the half. Remember? And this is 81 becomes 3 to the fourth. Then we simplify all of it into just one base. Okay, combine all of them together that we can. It becomes 3 to the x plus a half equals 3 to the half x minus 3 over 8. And now we just simplify that. And remember, when the bases are the same, then the powers have to be equal. So therefore, x plus a half equals 2x minus 3 by 2. And now when you simplify that, you get x equals 2, and that's your answer. And remember to always verify. It just helps you check. You don't really need an exponents, but you will need to verify in some of the other cases. The second type of exponent solving is when you can't make the same base. When you can make use normal exponent solving, now you need to take help of logs. This is why we didn't do this last year. So now there are 2, 3, 6, so many different bases. What we do, we log both sides. When you log both sides, you can use log laws to kind of separate it. Okay, and it becomes log 2. Since these are being multiplied, it adds log 2 plus log 3 to the x equals, well, whenever there's a power, we can just take that power outside. Just like this, we can take the power outside. It becomes log 2 plus x log 3 equals 3x log 6 minus log 6. Now that we simplified all of the logs, now we take all the x ones on one side and the normal ones on the other side, and it becomes log 2 minus log 6 equals 3x log minus x log 3. Now we factor this x out, okay, like that. And then to isolate this x, we divide it. Now we have this big equation, but it's nothing we can just plug into our calculator and solve. That's all you do. You plug it into your calculator, you solve it. Now with log solving, the first case is when there's logs everywhere. Okay, so an example of this is this equation: log 2 x minus 2 minus log 2x equals log 2 3. So this is exactly like what you did with the first case of exponents. Okay, you make the same base. All you do is you turn everything into one log on both sides. Then you drop the logs just like you drop the exponents in exponents, solve for x and verify. So with logs, it's very important to verify, because sometimes you get the answers that make the argument, this argument, remember it can be negative. Sometimes you get answers that make it negative. So first we combine, first step, simplify it into one log. Okay, so we use log laws, simplify it into one log on both sides. This side is already into one log. Then now when the base logs are same, we can drop the logs, and then we solve for x. Okay, and we get x equals -1. But we have to verify our arguments. By that, I mean these arguments. Wherever there's an x inside a log, we have to verify so to make sure it's not negative. Well, if we plug -1 in for the first one, we get -1 -2, which is -3. For the other one, it's also -1. So uh, even one of the logs not being correct makes the whole answer wrong. Okay, so we didn't even have to check this, or we didn't have to check all of them, but it's good to check all of them just in case. Okay, so we didn't -1 doesn't work, hence there's no solution to this problem. Okay, so make sure with logs especially, always verify. Now the second case is where not everything is logs. Okay, not, or when not everything is the same base, right? Just like how in the other case of exponents we turned it into a log. Well, now we're doing the other way around. Now we're turning it into exponents. So the steps to follow are: we bring all the like terms, in this case it's all the logs, to one side and the numbers to the other side, simplify it, turn it into exponents form, solve, verify. Okay, so we bring everything to one side, it becomes log 6 x plus 3 log 6 this, and we turn it all into one log. Okay, now all this is saying is 6 to the power of 1 is whatever this is. Okay, so we can write that out, and it becomes 6 to the power of 1 equals x plus 3 x plus 4. That's all logs means, right? Remember? So now we have that. It's just another quadratic. Make it 0, solve for it, and we get x equals -6 and -1. But we're not done yet. We have to verify. So when we verify -6, we find that it makes our arguments negative, and so it cannot be an answer. When we check -1, it works. It's just another positive number. So our answer is x equals -1. Okay. Now the last part is word problems. So there's four types of word problems that can come. The first one is growth decay. This you can find in the exponentials unit. So an example word problem I have is Hardy bought a new car for 24,000. Each year the car loses 18% of its value. So find its value in 5 years. How long until it's 4 times less than the original value? Whenever you see a percentage or like half value, double, something like that, you don't see any logs, okay? Then you know it's a growth decay question. Because the other types, you're either going to be given a log equation or it's going to be a compound interest. If it's not a compound interest, not a what do you call it, log equation, then you know it's a growth and decay. With growth and decay, this is kind of a formula for it. It's not going to be given to you, it's not on the formula sheet because it's pretty intuitive. It's just your final amount is going to be your original amount times uh 1, which 1 is equal to 100%, plus or minus or your rate depending on if it's growth and decay, which in this case it's loses 18%, so it's a decay, so it's going to be 1 minus 18% or 1 minus 0.18. Okay, and to the power of t divided by interval. So t is the number of years, right? But if we just have t, okay, then it's gonna be to the power 1 per year. That means per year. But we're trying to find a thing where whenever we plug in 2 for t, our answer should be 1. Okay, because every 2 years the car loses its value. So we divide by whatever the interval says right here. So the equation becomes, well, for the first part we have to find the value in 6 years. So it becomes, our value is original 24,000 times 1 minus 0.18, as we discussed. The time is given, so it's 6 years, and divided by our interval, which is 2. We plug it into our calculator, solve for it. The other question, how long until it's 4 times less than the original value? Okay, so our final is 4 times less than our original value, so it's 24,000 divided by 4 equals 24,000 1 minus 0.18. Now the thing we're looking for in this case is t. Okay, so we get this equation after simplifying. 1 over 4 equals 0.82 t over 2. It's just one of those, what do you call it, exponent questions that don't have the same base. So we log both sides and we solve for it. All this stuff we've done already. The second type of word problems is the log equation problem. In this case, you're given a log equation and asked to do stuff with it. Most of the time, it's gonna be like a something divided by something zero, and you have to figure out how many times stronger one thing was. So the magnitude of an earthquake is defined by this equation. A is amplitude of ground motion, and A0 is amplitude associated with a standard earthquake. So A0 is a constant that we don't know. The magnitude of the earthquake at its epicenter at its origin was measured to be 7.7, while in the nearby city it was 5.7. How many times stronger was the earthquake on its origin than the city? Okay, it's going to be a question like this. What do you do is you plug everything that you got into the equation. So the only thing you have is the magnitudes. So you plug it in and you're trying to solve for the amplitude because in the end you're always comparing whatever's inside to find how many times stronger it was. So you're trying to look for the a values, not the a0. So we solve for a1. It's log, so that means it's log base 10, remember? So it becomes, all this is question is saying is 10 to the power of 7.7 is a over ao, and we're solving isolating a, solving for a. So we multiply the a on the left side, and now since we're comparing these and ao is the same for everything, it's going to cancel out. Okay, we do the same thing here. We get a2 equals 10 to the power of 5.7 ao, and when you compare them you divide them. So as I said, the aos cancel out. We're left with 10.77 divided by 10.5.7. When you're dividing exponent laws, you subtract the powers, you get 7.7 minus 5.7, which is 2. So it's 100 times stronger. Okay, now the last type of question you can found, or well, the second last, but it's the same category, is compound interest. There's two types of compound interest ones. One where it says it's just a normal one and you're getting an equation like this. The other one is when it says continuously. That's when we have to use e. Remember e? This is the only place where we actually need it, and you get the PERT formula. So with this, a is our final amount, okay? P is our principal, which is our original amount. One is just, like I said, with the growth decay, it's just 100%. It's just one. R is our rate. T is our years. And N is, now this is kind of tricky. It's our interval. It's the number of times per year. Okay, so in this question, Our principal is 1,000. Okay. Our rate is 0.5%. So it's 0.0 zero 5. And our time for the first question, I guess, is years, is variable. But our n, our number of times per year, it says bi-monthly. Bi-monthly means twice a month. So how many times is that a year? Well, there's 12 months in a year, and bi-monthly is 2 times 12, so it's 24. So for the first question, find its value in 2 years. Oh, this is supposed to be a 2. Find its value in 2 years. Oh wait, I have the different question. Oh, I guess just look at this question. The only thing that's changed is our rate and the other stuff. Okay, so we just plug the numbers in. This is our principal rate divided by an interval. Okay, we have the years and we're just solving it, and we get this after plugging it into our calculator. For the other question, how long for the investment to quadruple? Well, once it's quadruple, it's gonna be 4,000. So we get 4,000 equals 1,000 plus the whole thing, and now we're solving for t again. Now it's another one of those exponent questions with different bases. So we log both sides, and we finally solve for it by plugging whatever we got into a calculator. The fourth and the last type is the continuous ones. Okay, with this one, it's just a different formula. Everything stays the same. Okay, it's a way like simpler formula. It just has e in it. This is our principal. This is our rate. This is our time, and yeah, we just plug stuff in. So $5,000 investment, rate of 8.4. Find the worth in 10 years. Plug everything in. 5,000, 0.084, 10. Plug it into calculator. Solve. How long will it take for it to double? Well, when you double 5,000, it becomes 10,000. This simplifies to that. And now, you know how you log both sides? Well, now with E, the only thing that's different is because it's E, you log both sides. So you log base E both sides. So ln 2 equals ln this. With power, the power rule, the take it the power outside rule, log law. Okay, it becomes this. And well, the log of itself, let's say log 2 of 2, log 3 of 3. All of these equals 1 because it's saying 2 to the power of what is 2? Well, 2 to the power of 1 is 2. 3 to the power of what is 3? 3 to the power of 1 is 3. Just like that, ln e is just log e of e, which is just 1. So ln e becomes 1. And we get t equals, when you isolate t by dividing 0.084, you get this. And yeah, and that's it for exponents and logs.